Hello, everyone. My name is Callum Treagaskis, and I'm from Scotland. And today I'm going to be talking a bit about dynamical modelling of avalanches, and a bit about my PhD, which I did at the University of Manchester. I'm now a postdoc at the NGI, and I'm still working on dynamical modelling. So I thought today we could do a talk to tell you a little bit about what I'm working on and how, and then also what sort of things we need for this problem. So I'm a mathematician by background, so there are going to be a few equations today, but hopefully subsidized with a few pictures as well. Okay, so what you see here is a large snow avalanche at Rugfon, which is the NGI's large-scale testing site for snow avalanches. And there's a few properties that we see here. Once it restarts, then we can have a chat about them. So here we see there's lots of snow in the bowl, and it can activate. So here it's set off by some explosives, but there's snow lying on the mountainside. And this is going to be a crucial part of what we talk about when thinking about how we are going to model these avalanches. So we have this sort of static snow on the mountainside. It changes phase and starts to flow. And then we get this sort of liquid-like moving mass. And then we get this propagation of the powder snow cloud on top. And then the avalanche comes down and then it runs into the big barrier, and then it changes. And we have all sorts of research questions about how we can model this and what we do. So here we have dry granular flow. Can be used as an analog for large-scale avalanches and debris flows. So we have this problem that we only get a few avalanches per year in certain sites, and then if we want to start following, like investigating properties in detail, then we need to use things that are similar in order to take it to the lab and do research on it. So in Manchester, we have a small-scale lab for granular flow. And granular flow displays many of the same properties that we see for gravity mass flows in general. For instance, if we see across this slide, we have like front instability. We see that there's a propagation of waves, and the waves have certain properties. We get moving parts and static parts, for instance, the formation of static levees at the side of a flow. We get exists snow already on the mountainside. We can have existing static material also in the lab frame that then gets entrained into a moving flow. And then we have this sort of activation of thicker material that then starts to flow. So this gives us a schematic representation of what we view as a dense granular avalanche. So we have these sorts of properties that we're going to need to model. We need to model how the basal topography changes, but we have a free surface. We then need to describe the thickness of the avalanche, which here is described as H. And then we have the material properties of the flow, for instance, the density and how that is made up. So there's a sort of intrinsic density of all the grains that make up the avalanche, and then how much space is surrounding them. So what do we actually want mathematically from an avalanche model? It becomes really important to capture the real world physical properties. So we do want it to be realistic. We want the equations ideally to be fast to solve. If we throw everything at these equations and work out exactly what's happening, grain to grain collisions, then these becomes very impractical. It takes months to set up a simulation, and then you might take several days on a supercomputer cluster in order to solve. And although we learn things about the physics of such a flow, what we can't then do is applications such as like hazard mapping over large areas, or if there's even a site-specific thing, then it's going to take a lot of time and resources in order to solve for that. So what we want to do is try and make simplifications and approximations that maintain the realistic behavior, and so that we can make progress, and also for these sort of wider scale applications. And we want it to be useful. So that means that we need it to be integrable into existing systems and also provide us with useful information that we need for such things. So if we're making a dam, say, then we need it to be able to tell us like realistic speeds and realistic thicknesses and how that's interacting. So like I was saying, there's sort of different mathematical approaches to how we model a granular flow. And that is to model either at the very small scale, where we model grain interactions, how they collide, how they bounce off each other, how they shear past each other. And this is great for understanding things at grain level. However, it becomes very hard to scale up. So what we tend to do is our first approximation is to treat the flow as a continuum. And this helps with the scaling problem, but we lose physical information about how the grains actually collide, and we're sort of making an approximation. So this is sort of the first of steps, what we take towards actually modeling an avalanche. Okay, so my PhD was a bit of a mixture. So like I was saying, I come from mathematics background, but my supervisor was very keen on taking people who have a more theoretical background and then making them do more people from a theoretical background and then making them do more experimental stuff, and taking people from experimental backgrounds and making them do more theoretical things. So this is supposed to help us broaden our views of how these things work, and then we hopefully can then combine all of this together into a project. So I looked at 3 research topics during the course of my PhD on granular flow. The first was on obstacle interaction and how the inflow conditions and it interacting with an obstacle, and then how the flow changes around the obstacle. And then we're looking at how the front instabilities of an eroding granular flow, and what we see is instabilities that are generated locally just to the front of an avalanche. And then the last topic I looked at was granular deposits and wave formation on varying basal topography, which was looking at how the interaction of static and moving material changes based on the varying topography on a mountainside. So we're just going to do a quick overview just to tell you a little bit about how the maths actually works. So this is where the equations come in, but hopefully give you a bit of an insight into what we actually do with the equations in order to build up an avalanche model. So this is going to be a very fast run through some continuum mechanics. So first of all, we take this blob. And now we've got to make this blob behave like a snow avalanche. So how do we do that? We need coordinate systems, and we need to be able to explain how this blob deforms. So we take this, and then we look at the deformation. Then we need to say, mathematically, how does the bits of the surface change? So this is area elements. And then how do volumes actually change, which is... And then we can say, if we know how area bits change over time and how volumes change over time, then we can start making equations for deformation. This allows us to take a material. So we have this material and it has mass, which is the sum of all these sort of density points across its volume. And then what we do is we say that the mass has to be conserved. So if we have a mass and it's and then we say it's changing over time, and then we need to make sure that there's no added mass, that the mass we started with things. So this is going to hold our volume. So then using these sorts of mathematical techniques, we can create these formula for conservation of mass and conservation of momentum. So this is just Newton's second law written in full generality, where we have the change in the momentum is equal to the sum of all the forces. So we have the body forces and also the contact forces. So how do we actually specialize this for granular materials? Is that we need to look at the stress. So we have got these equations that are in full generality for how things deform in 3D, but that doesn't give us enough information to actually solve them. What we need then is how the material actually behaves, and this is then given in terms of constitutive equations. So we have this element in the equations here that then needs to be described, like how the material actually acts, and then when we add that in, then we should be able to solve the equations. So for water and sort of fluids in general, then this is how we do it. We say if it's stationary, there's going to be a universal pressure field, and then that's going to, it's not deforming when it's stopped. But then when it's moving, then we have the stopped part, and then also how it changes. So this is the deviatoric stress. So this equation here then gives you the Navier-Stokes equations. And we do something very similar for the geophysical flows. So we normally consider them to be plastic, so that there's some threshold that it needs to get over to start moving. And there's sort of two different ways that we normally do that, either through viscoplasticity or Coulomb plasticity. But that's getting into the more technical things, but really what we focus on is how the friction changes, and then how the material actually flows. So a lot of the programs that you'll have seen for snow avalanche modeling, such as the one that's in-house, NGI, uses a method of transport Velame code, and then RAMS uses similar things. But here we have a constant Coulomb friction, and then we have a turbulent term. But for modern granular flows, we're going to use a thing called the mu of I rheology. And this is how it's put together, but it's a bit less important to talk about the details right now. But what we're actually doing is we're taking what's happening at the grain level. So this sort of grain-to-grain interaction that I was talking about earlier at the small scale, and then we're trying to make continuum approximations from that. So we do these discrete element simulations for how grains actually pass by each other using these sort of detailed numerical experiments. And then we look at how that actually changes and what that means for the friction in a continuum sense. So this is going to add more information in about how the granular material should flow. And then what we find is that even if we do that, we're still missing some extra information. And so what we can do is take a sort of empirical approach and just measure what's happening to static material and how it transitions from static material to flowing material and vice versa. And then we can sort of use the elements from the mu of I rheology, which is this mu d, and then also add in this sort of transitioning behavior things just as an extra. And this is going to give us a friction description that's going to try and match better what's happening for a realistic granular flow. So we add all this in, and then we need to make it so far everything's been done in fully 3D, but what we need to do is make a further approximation so that we can scale it up to the size of a mountainside. And the way we do that is to average through the depth. So there's a small parameter that we need. So we sort of consider that avalanches are much, much, much longer and much, much wider than they are tall. So this is important because that means that if we take the aspect ratio from the thickness, then that's going to be really small parameter. And in mathematics, to make approximations, we really like small parameters. What we want to do is we want to expand out, say that all powers of that small parameter, we can just get rid of them. They're less important than the big ones. So this is what we do, and we end up with this, which is the full 2D depth average model from the mu of rheology, which is a full granular fluid description. So it's the important thing about this is that this is actually a simplification. So although it looks a bit horrendous, but we can actually solve this, and then we can actually scale this up to the size of a mountainside, which is the important properties. So this is where we get into what my research actually looked at, which was sort of obstacles as avalanche protection measures. So here, historically, we need to protect the both infrastructure and the people living in mountainous areas, and this becomes very important. So how do we actually design mitigation structures that are effective against avalanches? So we need to understand sort of two things, both how to design and build these mitigation things, but also how the avalanche actually changes around them. So this has been looked into with granular flows. And what we see sort of from previous literature is that everyone's sort of done this so that it was really fast flow. So we have these super fast flows going down sort of slippy, like a slippy plane. And then we sort of see things like a bow shock forming in front of the obstacle, which dissipates some of the energy away from the impact. And then we get this sort of static region of buildup of grains in front. But what we find is that if we look at what's happening at a rough bed, then we can recapture for fast flows sort of on steeper planes, that we still get this sort of buildup of static material and the bow shock, but we can also get much slower avalanches too. So if we're looking at what's happening in maybe a runout zone or maybe a more dense avalanche that's moving a bit slower, then we get completely different behavior of the avalanche. So in this case, you don't get any bow shock forming, and instead you get this weird upstream region, which can go all the way back upstream. So this is backing up, and then it can change where the flow might go. So this is dependent on the inflow parameters, and so we can take properties that we can measure, such as the thickness and the speed, and then we want to see what is the factor that changes between these two cases, between the sort of upstream behavior and it flowing down below the obstacle. Do this, and we also find that if we let the avalanche run out, then it leaves behind a deposit, and we get raised levees bounding the region downstream, and then we're going to get these sort of large regions of piles of material upstream of the obstacle. So we can measure this in the lab, and we can look at it with some laser scanners that tell us about the thickness, and we can try and then model what's going on. And then lastly, what we need to do is model the material so that we can apply our equations. So what we need for that is to do some tests about what the speed of the avalanche is and what the thickness is, and then how it leaves a deposit behind. And so we do that, and then we can apply our model. So this gives us our simulations which show us how an avalanche is flowing down with different fields. So here on the far left, we have the thickness field for the avalanche, and then going right, we have the downstream velocity, and then the cross slope velocity. So this is how it's spreading. And then the Froude number, which is our parameter that we need for indicating whether it's going to form a bow shock or not. And then at 45 seconds, what we do is we stop the inflow, and then we're going to see what happens as the avalanche runs out. And then that leaves behind static material. We might get sort of these waves forming, erosion deposition. And then we're going to end up with raised static levees beside the vacuum region. So this we can then compare to the experiments. We do quite a good job finding what the shape of the pile upstream of the obstacle should be, and also these raised levees in the downstream direction. We can also do this for slow inflows, and then we find that we can capture a bit of this upstream region, but maybe not entirely, but we capture an awful lot of the other features. And again, we can compare that to experiments. And the last part of that study was to look at how this pile actually forms and whether we can sort of use other techniques from mathematics to describe that. So there's an idea of what is the maximal pile that can be built up against an obstacle. And this is important because we can compute what the maximal pile should be. And what we find then is that when an avalanche impacts an obstacle, it doesn't behave exactly as what just a maximal pile sitting up against it should be, in that we have this sort of pressure impacting the obstacle, which then raises up this pile. And then we can show that with the theory. So that was one project that we looked at, and then I'm going to talk a bit about the other ones. So this one is to do with front instabilities of an eroding granular flow. And if we look at this debris flow from Shaanxi during a surge, what we find is that there's sort of instabilities that are localized just to the front of the avalanche. So here we're sort of seeing a swirling that's just completely local, just there. And if we go to the lab, we can see something similar. So if we run sand down onto something that's erodible, then we get these ripples forming just at the front of the avalanche. And if we look at them using high-speed cameras and some sophisticated lighting, then we can highlight and work out what the sort of speed of these ripples are in comparison to everything else. And while there's theory for how surges form in granular flows, no one really knows how these ripples form. And what we know from the theory is that if we have this surge and then we have these waves, that they're supposed to travel faster than the main bulk flow of the avalanche. So we can calculate the bulk flow of the avalanche, which is this red line, and then we see that these ripples actually move slower than the bulk flow of the avalanche, which is unusual, and that means that they're propagating backwards from the front. Whereas the roll waves that you see that then overtake the front, they're definitely moving faster and keep with the theory. So we were trying to see whether our model could capture this. And what we found is that for given certain thicknesses, we can generate instability just at the front. However, these waves aren't propagating backwards, so they're only propagating forwards. So this was a bit of a study to look into this, but we probably need more sophisticated modeling about how entrainment actually takes place in the flow in order to describe these sorts of properties. So what we see in radar of large-scale avalanches is that the entrainment doesn't happen full depth all at once. We might get this sort of stepping as successive layers maybe break down and are brought into the avalanches, or there might be other things going on. So we need more sophisticated modeling in order to capture such a feature. And then the last project was looking at granular deposits and wave formation. So what we find here, movie isn't working. There we go. So if there's a deposit already in place on the slope, then we get completely different behavior to if there's not. So this is an important factor that we need to consider, what is the role of deposits on the mountainside to what actually happens as the granular flow is propagating. So to do this, we looked at a sort of idealized topography, which is just sort of a change in angle. And then we considered like what happens to deposition, how do things stop if they're going over such a transition? How are things like roll waves influenced by the topography? And then if we look at 2 dimensions, then do we get different growth and decay depending on how much transition we go over? So we can look at this and we see the flows come down, and then at 30 seconds, it's going to shut off the inflow. And what we find is that despite the fact that we have these much faster flows going into on a steeper plane, and then we transition to a less steep plane, that we get still a steady transition in speed, which is sort of interesting. But then when the deposit comes down, the black dotted line shows our prediction of where it should be, and we find that we recapture that. So that's good for our model. It shows that we can sort of capture how it's supposed to deposit. And then if we look at waves, so here we have a wave train coming into our transition. And then we see that the waves actually can change properties from being roll waves, which are sort of continuous sets of waves, and then we get maybe static regions in between the waves. And this might explain how surges develop in debris flows. And then lastly, looking at the sort of growth, and then we can go over the transition, and then it can decay away, but we're capturing things such as the front of the head of the avalanche, and also how the levees form at the sides. So in the last couple of minutes, I'm going to talk a bit about how I'm then taking this work and then we're applying it a bit further. So we're trying to look at fluidisation and these sorts of other things about phase change and for maybe more relevant for snow avalanches. So this is how we're sort of using these techniques from granular physics, and then we're wanting to apply them to snow avalanches and make that more realistic. So how we go about doing that is to look at these sorts of properties that we talked about before, but maybe try and specialize them more specifically for snow. So we're wanting to look at how the flow moves, and then we want to look at the material properties of snow, how the rapid collisions work, and all these sorts of properties. And then if there's phase changes, which we sort of know from radar data of the snow, is that we're getting this sort of entrainment, and then it forms a dense core, but then we might get these sort of fluidized regions at the front and on top of the flow, and before it generates a powder snow cloud. So these are the sorts of properties that we're going to try and model during my postdoc. So why do we actually need this extra complexity? So the dense flow is where most of the mass is in an avalanche. However, the powder snow cloud can still be very destructive. And so due to the increased mobility of fluidized avalanches, the powder clouds, they might take different paths on the terrain, they might travel further, and the powder snow can still be very destructive. So an example of this is a powder snow cloud that rips the roof off a building in Switzerland in 1991, and it was just the powder cloud. The dense flow didn't get anywhere close to the building. So this is important. So how do we go about trying to model this? So we're sort of looking at various options in the group here, the NGI, and we're trying to sort of take an approach from granular physics. And then we want to maybe look at how we can use sort of theory from granular physics in order to track different media throughout the bulk flow of an avalanche. So if we take that there's sort of air within a snowpack and then treat that as a grain that's segregating up through the flow, then we might be able to sort of capture some of these properties of fluidisation. Another option may be to utilize an approach used in geotechnics, and that's to sort of look at the pore pressure, have a sort of excess pore pressure term, which is then governing the sort of escape in air up through the snowpack. So just to leave you, developing a model is a continuous process. As we gain more information from the science, we want to update the existing models, and as computational power gets better, then we want to sort of include these new techniques and make them better. So this is so we're always trying to adapt and change, and we want to make it sort of integrable for new cases. But one of the key takeaways is that at this time, a lot of we can have a lot of extra complexity in these mathematical equations, but approximations are still a necessity in order to actually solve something on the geophysical scale.